Good morning, students. I am Professor N.V.S.N. Sharma from NIT Warangal. In today's class, we shall discuss in detail the architecture of a radar transmitter and a receiver. In this, we are also going to cover discussion on radar antennas as well as displays. So let us see how a transmitter must be designed first. So the total coverage will be first introduction, radar transmitter, waveform generator and receiver, the architecture of the radar system, radar antennas, displays, and then we are going to have summary of all the things. So in the slide shown here, you are going to see the complete block diagram of a radar transmitter cum receiver. So in the first, we are going to discuss the highlighted blocks of this slide. They are the waveform generator, transmitter, receiver and the duplexer. We can classify a radar system as two parts. One is the low power section and the other one is high power section. The low power section will be there in the transmitter as well as in the receiver. The high power one will be only at the higher end of the transmitter, wherein we are going to have high power amplifier, duplexer, etc. So here the low power section will be the starting point in the transmitter, wherein the required waveform will be generated and a low amplitude signal will be produced. Similarly, in the receiver, we are going to have a low noise amplifier in the starting point, and then the processing unit of the receiver will be there, which will be working at very low power. After doing all this, we are going to get the signal output that can be given to a radar display. Then let us see how the radar transmitter will be designed. The design will be based on the basic radar equation. As you see in the slide, the radar equation can be given in terms of the signal to noise ratio as shown, where the different parameters are explained on the right side. So here the average power, the system noise temperature and the system losses must be taken into account while designing the transmitter. And if you want a high signal to noise ratio, we need to transmit very high power and see that the system losses are very low, and receiver noise temperature must be as low as possible. So these three parameters affect the design of the transmitter cum receiver. Now let us discuss in detail the design of this high power amplifier in the transmitter. Here it's not going to be one amplifier. Generally there will be 2 or 3 amplifiers placed in cascade. As you see in the slide, the low input signal from the waveform generator will be given to first amplifier PA1, which will be amplifying to a certain extent. Then that will be given to another amplifier PA2. These two amplifiers will be normally linear amplifiers, which will provide sufficient amount of amplification. Then the third one is going to be the high power amplifier, which is normally going to be class C type. That means it gives very high power gain, but a bit of distortion is going to be added to the signal. But here the signal is going to travel in the space and hit the target, come back from the target towards the receiver. So as it is going to travel in the free space, considerable amount of noise is going to be added anyway. So some amount of distortion can be tolerated as though it is introduced by the free space. So taking the advantage of this class C amplifier, which gives very high efficiency, a high power amplifier will be normally designed with the class C mode. So here we can expect efficiency greater than 80%. in these amplifiers. But the heat dissipation and other problems are to be handled carefully. So here we have two low power amplifiers in the preceding stages, or what we call them as driver stages, and the last one is going to be the high power amplifier. Here the requirements are going to be low noise and minimum distortion to the input signal. So here we will see how this high power amplifier can be introduced into the radar system. If we are going to have separate antennas like in a phased array system, we can use separate amplifiers for each of the antenna as shown in the first diagram. So here every amplifier will be separately fed with the DC supply and the signal input, and the output of this amplifier will be directly connected to the antenna. This may not be so in the conventional radar systems where a single antenna is going to be used. So in the figure 2 you will see that several high power amplifiers will be used in parallel, and the output of all these things will be combined in a parallel combiner. Then the output of that will be given to this single antenna, which is going to radiate hundreds of watts or even kilowatts of power. So here the addition of the power output from the different power amplifiers is going to be a difficult task, but a single antenna can definitely radiate all this high power very effectively. So there are plus and minus points of using several amplifiers together or individually to different antennas. So by combining several amplifier outputs together, we are going to incur some amount of combining loss, and also there will be increased amount of complexity because high power, high frequency signals combination will be a tough job while taking care of the phase synchronization. So we will now see in this slide the different types of power amplifiers available. Vacuum tube type amplifiers are one class, the other ones are solid state amplifiers. If you are going to compare, you will see that the output power can be very high in the case of vacuum tube amplifiers. Normally klystron amplifiers we are going to use are TWT amplifiers. In this context, we can get power output of the order of tens of kilowatts or even to the extent of megawatt of power. If you are going for several antennas together working like a phased array, we can consider solid state amplifiers as the choice, wherein the power output is going to be low. That means it's going to be in the range of tens of watts or even hundreds of watts. Accordingly, if we see the cost per unit, for a single power amplifier of vacuum tube type, the cost is going to be in hundreds of dollars. But we need very few of them in that. Whereas, if we go for solid state amplifiers, which can be used with multiple antennas, the cost can be very, very low, of the order of tens of dollars or even hundreds of dollars, depending on the power output. But you need multiple numbers for this. So the cost per watt of power output, if we consider, then it's going to be $1 to $3 when we go for vacuum tube type devices, and it can be variable in the case of solid state amplifiers. Then it's not the cost or the power output that decides in most of the cases. The size also matters. So here, if we see the vacuum tube type devices to be used in a radar, it's going to be very bulky and heavy also. Whereas if we go for a solid state amplifier like a gun amplifier, etc., or other types, it's going to be very small size and the weight is also going to be very much minimal. So whenever we consider portable radar systems, we can easily consider the solid state amplifiers as the good candidate for that. Then if we go for the application point of view where we can use these amplifiers, vacuum tube amplifiers are good when we can go for a dish antenna or a passive array of antennas to be used with this radar system. But whereas the solid state amplifiers will be very convenient whenever we are going for an active phased array or a digital array radar. In this view graph, you can see the power variation at different frequencies by the two classes of amplifiers. As we see in this graph, at high frequencies and at high powers, the vacuum tube type amplifiers will be the rulers of that region. Whereas at low frequencies and at low power outputs, if we require, then solid state amplifiers will be the right choice. And in between, like medium frequencies or medium power levels, both of them will compete with each other and the user has a choice to choose between them. So the types of power amplifiers that can be used in these radar systems, if we can see what are the choices we have. In vacuum tube amplifiers, we have the choice of klystrons, that is two cavity or multi cavity. Then traveling wave tubes, wherein mostly we will go with helix type of traveling wave structure for them. If we consider the solid state amplifiers, solid state power transistors can be used for these applications. Then the criteria for choosing the high power amplifiers will be what is the average power output as a function of frequency. Then the next criterion is going to be total bandwidth of operation. Then duty cycle also matters, because how much peak power we can derive for an average power of this much is decided based on the duty cycle. Then what is the gain we are looking at, and reliability aspect also must be taken care. Here we are going to consider for reliability the MTBF as the benchmark. The mean time between failures of the active device is very, very crucial in this. Similarly, there are several, but these parameters will gain prime importance in the selection of the power amplifier. Here in this diagram, you can see one particular radar which has been designed in the early 60s with the klystron tube amplifiers. You can see from the specifications of that the peak power is in the range of 3 megawatts, whereas the average power is only in the 120 kilowatts region. And the beam width of the antenna is 0.6 degrees, whereas the size of the antenna is of the order of 84 feet. Here they are going to use 2 klystrons for the total amplification, which is normally kept in the hut below the radar system. And if we go into this radar transmitter part, you can see different components that will be required for this. And here there will be one klystron which will be operational, and another klystron will be kept as a spare tube, and in case of necessity or emergency they will switch over between these two tubes for continuous operation. This type of klystron will be produced at very few locations in the world, and Varian company is a leader in this. And the cost of the tube is given as $400,000 per tube, and the size is approximately 7 feet by 1 foot. And the peak power required for the drive level is going to be of the order of 600 watts. These are the numbers which are very much useful just to have an understanding of how much cost is going to be involved in the design and operation of a radar, and what are the other issues involved in this. The engineer can have an idea from this. Here the high power is required so that from the hut onto the top of the antenna the power can be driven with full efficiency, which goes to a length of the order of 200 feet. So through a waveguide we are going to send this power to have very low loss. Here you can see different vacuum tube devices used at different frequencies. For an S-band frequency of operation, a TWT is shown first, and in the second diagram you can see for the same type of job how an X-band device is going to differ. For this X-band device, the specifications are also mentioned, wherein the gain is going to be of the order of 50 dB. Here you can see different power amplifier modules which are used for different antennas. Using a rake receiver type of thing, we can have several amplifiers placed in a rack for ease of operation. So here we have 14 channels with 140 kilowatts of total peak power coming out of this amplifier section, and which are fed to the antenna array kept outside this. Here you can see a phased array radar, very popularly known as PAVE-PASS, and you can consider that this is the first all solid state active aperture electronically steered phased array radar operating at the UHF band. And in the next diagram you can see the solid state amplifier which gives to the power of 340 watts or so peak power in a small box as shown. Here we are going to see what is a duplexer and what is its job and what are the other issues concerned with it. So before we go into that, let us see what is the requirement or what is the necessity to go for a duplexer. Here we see that a high power pulse is transmitted by the antenna, and now the antenna will be waiting for the echo from the target, and this echo will be received by the same antenna, and it should be now directed to the receiver, and after certain time again the transmitter must be connected to the antenna to transmit the next pulse. So as shown in the slide, the blue colored pulses must be transmitted first, one after the other with a certain amount of gap. During the gap time, that is the receiving time of this antenna, the signal must be sent to the receiver. Then it will be processed mostly by converting it into digital form. So a duplexer must be able to switch the antenna between the transmitter during the transmitting time and to the receiver during the receiving time, and this total time must be the pulse repetition interval, PRI. So a duplexer must be able to switch the antenna connection between transmitter and receiver very effectively. Here the power problem is the main concern. While the transmitter is connected, the antenna will get the power in the range of tens of kilowatts or even megawatt of power. Whereas when it is receiving, the antenna will be receiving the power in fractions of watts, maybe of the order of 10 power minus 24, minus 22 or so, which is very, very small compared to this. The receiver is highly sensitive to process these low power signals and give a very useful output. So the transmitter power should never be allowed to go into the receiver, because the power level from the transmitter is in the range of 10 power 3, whereas the receiver is sensitive to the powers of 10 power minus 20. So even if a minor amount of leak is there between transmitter to the receiver, it's going to be fatal, or the receiver is going to be saturated very easily. So to protect the receiver from this high power, a duplexer must be able to isolate properly. So that is the importance of placing a duplexer in the path from antenna to the transmitter. So when the transmitter is on, the duplexer must be able to guide the power from the transmitter to the antenna and protect the receiver completely. Then while the receiver is on, the antenna must be connected to the receiver and see that there is no loss or even a distortion to the signal. And a limiter switch is placed normally after the duplexer in the receiver link, so that by accident, if the duplexer fails to stop the power from the transmitter going into the receiver, the switch can give the second level of protection for this. And also against strong interfering signals, the receiver can be protected using this switch. Now let us see more details about the transmitter. Here the first block is going to be waveform generation. That is, here we will use a simple circuit to generate the required type of waveform, whether it is an analog signal or a digital signal. Then we are going to have the amplifier which will amplify this basic signal to the required level. Then we are going to upconvert this to the required frequency. So a carrier signal is separately generated for this, and after upconversion we take out the unwanted signals using the filters. Then we are going to have the required pulse shape and also the required level of power within that. So it can be a simple CW signal or a pulsed signal or a Gaussian signal, or in the latest radars it can be an arbitrary waveform also. So this signal is going to be given to the antenna and it will be transmitted towards the expected target. Then the target is going to scatter this energy in all the directions. A very small portion or a fraction of the total power is going to travel in the return path towards the antenna again. So the antenna, as it is waiting for the received signal, will be receiving this, and the received signal amplitude is going to be very, very small. To remove the unwanted noise, we are going to first send it through a filter. It can be a range filter or a Doppler filter or some other type. Then we are going to down convert this, or we are going to remove the carrier part in the received signal and then amplify at a low frequency amplifier. Then we will be converting this low frequency signal into digital form for further processing. So the waveform generator and the receiver share several similar functions. What are those things? The common blocks in the transmitter and receiver will be amplifier, filtering and mixing will be done. That is, the frequency conversion. In the transmitter part there will be up conversion, and in the receiver part it's going to be down conversion. So let us see some details regarding the frequency conversion concepts. How are we going to do it? So here for frequency conversion we require two inputs to this mixer block. One input will be very low frequency. So just for an example, we are going to have 0.1 gigahertz or 100 megahertz signal as the input. The other input is going to be from a local oscillator. Typically it can be 1.4 gigahertz. When these two are mixed, we will have both sum and difference outputs. By using a proper filter, we can take some output wherein we are going to get the up conversion. In this context, it's going to be 1.4 gigahertz signal mixed with the 0.1 gigahertz, giving rise to 1.5 gigahertz total up converted signal. When we receive this 1.5 gigahertz signal from the target, we are going to use again a local oscillator at 1.4 gigahertz to be mixed up with this in a down converter. That means it is also going to be the same device like the earlier case, but now the difference output will be selected by the filter. So 1.5 gigahertz input signal is mixed with 1.4 gigahertz local oscillator signal. So the difference between these two, that is the 0.1 gigahertz signal, will be coming out because of the selection of the filter for the difference signal. This can be easily down converted if required or converted into digital form for the processing. So the up converter translates the waveform to a high frequency, whereas a down converter translates the received signal to a low frequency. And waveform generation is less expensive at low frequencies, and the dynamic range of A to D converter is higher at low frequencies. Hence, the processing or the generation and other things, as far as possible, we will try to do it at low frequencies. But a high frequency signal is required for efficient transmission through antennas and to get proper or accurate information regarding the target. Hence, both the advantages are taken up by using these mixers at receiver as well as at the transmitter. Now let us see a simplified system block diagram of this waveform generator and receiver. The waveform generator is going to be a simple oscillator, maybe CW or a pulsed one. Then it's going to be amplified, then filtered properly to see that satisfies all the requirements for the up converter. Same local oscillator can be used in the transmitter as well as in the receiver blocks. So using a 1.4 GHz local oscillator, you can mix this low frequency signal of 100 MHz to 1.5 GHz by using a frequency selective filter. After this, we are going to use a high power amplifier. That means preceding to this high power amplifier, we have the entire waveform generator circuit for 1.5 GHz, which is now modulated already. The basic 1.4 GHz is generated by a local oscillator, and this additional 100 MHz signal is generated by a separate oscillator. So putting these two things together is what we got, this 1.5 GHz signal, which will be amplified to the required level using a high power amplifier. Then via a duplexer, it will be connected to the antenna. The received signal is directed to the receiver by the duplexer, and the first stage is going to be a filter to remove the unwanted noise. Then normally we are going to use an amplifier which will be a low noise amplifier, because the signal is highly corrupted with noise. We don't want the amplifier to add any more noise into it. Hence, separately designed low noise amplifiers, normally maintained at very low temperatures, will be used for this. The main purpose is not to add noise, but to add only gain to the signal. So though the signal gain is going to be less, we'll be happy with this because the noise addition is very minimal in this. After this, the signal will be sufficient level to go for down conversion. Using the same local oscillator as earlier, we are now going for a down conversion by selecting the output filter for the different signal. So the 1.4 GHz local oscillator signal is mixed with the received 1.5 GHz signal into this, and the difference between them is going to be the output from this. So your 100 MHz signal is now amplified by a normal amplifier. Then any unwanted thing will be filtered out by this. Now we have the information of the target available on the 100 MHz signal. So to process it efficiently, we go for A to D conversion and put these bits into a processor for removing the noise, distortion, etc., and to decipher the target coordinates accurately with this. So here the example is to show different stages of the waveform generation and the receiver. So multiple stages of amplification and filtering are used both in the transmitter and in the receiver. Here you can see different standard radars that are used and a simple block diagram of a radar. Here we have a waveform generator followed by a transmitter and a duplexer. The output is directly connected to the antenna. From the received signal of the antenna via a duplexer, we give that input to the receiver, which is converting it into a low frequency one, and this analog output is converted to digital form for further processing by this. This is the most conventional block diagram of a radar system, which is used in most of the radars that are shown in the slide there. Now we are going to see something about the radar antenna architecture. There are three types which are normally practiced. One is a simple dish antenna, which will be able to radiate very high powers and which will be rotated mechanically for different locations to identify the targets coming in different directions. So here we have the transmitter connected first to the dish antenna to transmit the signal. Then the antenna is connected to the receiver to receive the echo from the target. The advantage we are going to have is that it's very low cost and you can have frequency diversity because dish antenna can operate over a wide band. The demerits of this will be a dedicated function. That means if the antenna fails, the entire system must be shut off. Then, as there is mechanical movement to different locations of the scan area, the scan rate is definitely going to be slow and it requires custom transmitter and there are going to be high amount of losses. Going to the second type, which we call as passive array radar, wherein the power output from the transmitter is split to different antennas and providing required amount of phase shifts, we can see that the antennas radiate into particular direction of the incoming target. And if there are several targets, the antenna can be used to point the beam to different locations by simply changing the phase shifters without the movement of the antennas. So as there is no mechanical movement, the scan rate can be at very, very high speed due to the electronic methods used. So the plus and minus points, if you want to see about this, the plus points are the beam agility. That means beam can be placed to different locations with very much ease. And effective radar resource management is properly done in this. Whereas the demerits are higher cost, requires custom transmitter and high power phase shifters. Then the losses are going to be high because of use of multiple antennas. The third variety we have is active array radar, wherein the antenna is connected with the transmitter receiver modules and the power required for the antenna will be amplified by the amplifier connected at the back of this. The receiver is also going to be placed right there so that the received signal is processed to a first stage and then only down converted to the receiver. And hence we have multiple number of transmitter receiver modules connected to different antennas, and hence you can have a single beam or multiple beams simultaneously with this. So the plus and minus points of this active array are beam agility. Again, you can point out the beam to different locations very much easily and very accurately. Then there is effective radar resource management. Also there is low loss because the amplifiers and the antennas are connected back to back and hence there is no transmission loss. But on the other side, the demerits are the high cost and more complex cooling mechanism is required because so many amplifiers are working at a very small size, hence the heating effect must be taken care properly with this. Here, when we go for an active phased array, we can see here in this slide that there are going to be several transmit receive modules, and after this there are going to be phase shifters which will be programmed to see that the beam is pointing to different locations. There can be a single beam or multiple beams by properly choosing the phase shifter values. the TR modules will have separate transmit receive sections. The low power section will be directly getting the signal from the base, and after this it's going to be amplified. Then via a duplexer, the transmitter signal is connected to the antenna. The received signal from the antenna is going to be directed towards the receiver by the duplexer. The receiver will do some sort of pre-processing and then direct the signal back to the ground state. And hence you have several TR modules working simultaneously, and in case of failure of small number of them, the performance of the radar is not going to be disturbed much, and hence there is going to be graceful degradation of the entire radar system instead of a catastrophic degradation as in the case of a single antenna radar system. So a phased array is definitely advantageous in the operational point of view and in the amount of ease we have in the operation, whereas the cost of the system is prohibitively large because of use of multiple phase shifters, which are proprietary items. So many people would like to have phased array, but looking at the cost, they are a bit worried about the operation of that. Whereas the other side, the single antenna radar systems are very, very conventional. The technology is well established and mature, and hence many people prefer to go for them, but the flexibility or the ease of operation is much less compared to the active phased array radar system. We'll have separate transmit receive sections. The low power section will be directly getting the signal from the base, and after this it's going to be amplified. Then via a duplexer, the transmitter signal is connected to the antenna. The received signal from the antenna is going to be directed towards the receiver by the duplexer. The receiver will do some sort of pre-processing and then direct the signal back to the ground state. And hence you have several TR modules working simultaneously, and in case of failure of small number of them, the performance of the radar is not going to be disturbed much, and hence there is going to be graceful degradation of the entire radar system instead of a catastrophic degradation as in the case of a single antenna radar system. So a phased array is definitely advantageous in the operational point of view and in the amount of ease we have in the operation, whereas the cost of the system is prohibitively large because of use of multiple phase shifters, which are proprietary items. So many people would like to have phased array, but looking at the cost, they are a bit worried about the operation of that. Whereas the other side, the single antenna radar systems are very, very conventional. The technology is well established and mature, and hence many people prefer to go for them, but the flexibility or the ease of operation is much less compared to the active phased array radar system. Here you can see different phased arrays used at different locations, and the array system is highlighted in each of these diagrams. Here we are going to see a digital array radar architecture. Means the signal that is received from the antenna or from a group of antennas will be converted into digital form and then processed further. So here we have the signal combiners of 2 or 3 or multiple number of antennas. The output of these signal combiners will be analog signal, which will be processed, that means basically filtered out and amplified to a sufficient level initially. Then the signals will be converted into digital form. So all these digital signals from different sub-arrays will be combined into a digital combiner for further processing of this. So here we have the choice of taking up each antenna as a separate one, or a group of antennas together as a single antenna, or all the antennas together as one antenna itself. We can consider and take the output as desired. So simultaneously we can track multiple targets. Hence the same technology is being implemented in the wireless cellular communication system as well, wherein the base station has to track several mobiles in its surrounding region. So here in the cellular communication, this we are going to call it as space division multiple access system, or the third variety of multiple access. We have already in place time domain multiple access, frequency domain multiple access systems, and with the phased array system implemented at the base station, we are going to have the third variety, that is the space division multiple access. This is without any disturbance to the code division multiple access that is already in practice. So a digital on receive system is shown in this slide here. There are 14 digital receivers in this. So digital on transmit and receive. That is, here we are going to transmit the digital signals up to the antenna point from the ground station. That is, the basic generator is going to generate digital signals only, which will be amplified in a digital amplifier and taken up to the level required for the transmitter. So at the transmitter point near the antenna, we are going to convert these digital signals into analog form. That is, we are going to introduce the carrier into these digital signals and make them appear as though they are analog signals. These analog signals will be transmitted by the separate antennas, and on receiving these signals, again the analog signals will be converted back to digital form. Then they are all going to be combined for the required data using a digital combiner. So both waveform generation and receiver digitization are performed within each TR module. So there is complete flexibility on transmit and receive in this process. Let us summarize whatever we have learnt so far in this. The radar transmit function is accomplished in two stages. One is the waveform generation creates a low power waveform signal and upconverts this to the RF level. Then the second part is transmitter amplifier is going to amplify this to the required power level. Then the radar receiver performs filtering, amplification and down conversion functions. So the final received signal is fed to an A to D converter for digitization. And the radar transmit receive architecture is highly dependent on the antenna type. So centralized architecture is used whenever we are going with the dish antennas or passive arrays. And a distributed architecture is used with active array or digital array radars. Now let us concentrate on radar antennas. The fundamental parameters are what is the coverage, that is how much distance must be covered by this antenna system, and here the received power from the antenna is proportional to the r to the power 4, that is the receiving area of the antenna multiplied by the signal density available must be sufficient to see that the power is crossing the minimum detectable signal of the receiver. So that is one important parameter. The minimum signal is a very strict constraint on the receiver, and if this signal is very low, the cost of the receiver is going to increase drastically. So the antenna must be able to give sufficient amount of signal by placing a high effective area of the antenna. Thereby, even with low power density of the echo signal, we will be able to give good amount of input signal to the receiver by high effective area of the antenna. Hence, parabolic antennas are good candidates because they have very high amount of effective area compared to the physical area. Then the second parameter of interest is the resolution. What do we mean by resolution? It is the ability to recognize closely spaced targets. So here the beam width of the antenna comes into picture, and the beam width is inversely proportional to the area of the antenna in terms of wavelengths. So if we can put large size of the antenna, the beam width is going to be small and the resolution is going to be very much high with this. And the resolution what we require will be in the range of 1 to 10 degrees. The other parameters of the antenna that are of interest will be the size. The antenna size must be convenient to see that the radar system is very simple and less weight. So for a typical case like proximity fuse used in artillery shells, the phased array must be housed in a multi-story building for detecting and tracking objects in space. But that may not be possible, and size and cost are normally limited, and this is by the physical space and the amount of importance given to the radar system. Then, what are the jobs that will be done by these radar antennas? One is the beam scanning and the other one is target tracking. So to search for targets in a volume of space, we say that it is the scanning of this. So here the antenna may be moved either mechanically or electronically or both ways. In electronic scanning, we require that the antenna should not be moved, whereas the beam must be able to move to different locations. Whereas in mechanical scanning, the antenna will be moved to different locations by using motors, and the beam will be pointed corresponding to different directions. The inertia plays a very important role between these two types. In electronic scanning, as the antenna is not moved at all, only the beam is moved by electronic means, there is no inertia in that. Hence, the beam can be moved at very high speed. So accurate pointing is a requirement inherent in all radar applications that measure target location. So the radar functions can be classified into two varieties. One is a search, wherein to examine a volume of space at regular intervals to seek out targets of interest. Whereas in the tracking, one or more targets are identified already. We need to get the information of this target on continuous basis. So a high data rate is required about this particular target at different times so that we can predict its future position and eliminate that very effectively. So certain radar systems combine the search and track functions by time sharing the agile beam of a phased array antenna. Because of the great variety of radar applications, radar antennas are required to operate in many different environments. At fixed sites, the larger radar antennas are often protected by a radome, especially in the Arctic regions that experience heavy winds, ice and snow. The second variety is transportable systems generally require that the antenna be disassembled for transport. The third one is mobile systems, prepared to move rapidly from place to place and usually do not allow time for antenna disassembly. Marine radar systems, smaller antenna, larger transmitter than would be used in a comparable land-based application are recommended for this. The basic role is to act like a transducer between the free space and the guided waves of the system. And during transmission, concentrate the radiated energy into a shaped direct-to beam which illuminates the target in a desired direction. During reception, the antenna has to collect the energy contained in the reflected signal and deliver it to the receiver without much of a loss. And highly direct-to beam width is needed to achieve angular accuracy or resolve targets close to one another. With all this, let us consolidate the required parameters of an antenna. The parameters are peak power, average power, directivity and gain, radiation pattern, particularly the beam width and side lobe levels, polarization, cross polarization, antenna impedance, scan volume, scan time, pointing accuracy, finally the size and weight. Let us see these parameters one by one. What do we mean by this directivity? The ratio of the radiation intensity in a given direction from the antenna to the radiation intensity averaged over all directions. So as shown in this equation, the directivity of an antenna which radiates uniformly in all the directions, or what we call as isotropic radiator, is considered the lowest, that is 1. So the maximum directivity is defined for a particular direction, and this will be identified first. The directivity is normally given in dB scale, and the gain is directivity multiplied by the efficiency of the antenna. And this directivity or the gain is related to the effective aperture, which is very much useful for the receiving systems, and they are shown as the equations. The antenna radiation patterns, if we see, we are interested in certain parameters. The common parameters of interest from a radiation pattern are main lobe or bore site. Then we have half power beam width, in short known as HPBW, or some people call in different ways also. Then we have front to back ratio or F by B ratio. The final one will be pattern nulls or zeros of the radiation pattern. And these radiation patterns are typically measured in two principal planes. One is the vector field is E field parallel to the ground. The other one is perpendicular to the ground. So one is horizontal polarization, the other one is vertical polarization. If in a particular case, if we have both these polarizations and equal amplitude electric field vector is radiated, and if the phase difference between the two types is about 90 degrees, then we get circular polarization. A typical antenna pattern shown on a polar chart can be seen on this slide. Here, the different parameters of antenna are shown. One is what is that we mean by main lobe, what is that half power beam width is, what are side lobes, what is a back lobe. The 3D picture of an antenna pattern is shown in this slide. Here, with this 3D picture, we can see how a field pattern must be taken and how do we identify the main lobe and the side lobes in that. So nulls can be between the main lobe and the side lobes. We are going to see what are these patterns in two different planes for this, and a rectangular chart of this radiation pattern along with main lobe and side lobes is shown in this diagram. In this, we have side lobes coming up, and what are the problems we have with these side lobes we shall see now. In the transmit mode, the power is wasted through these side lobes. In the receive mode, the radiations from the unwanted targets can be received through these side lobes. So a radar for detecting low flying aircraft targets can receive strong ground echoes through these side lobes, which may mask the weaker echoes coming from low radar cross-section targets through the main beam. So side lobes are definitely a disadvantage point of these antennas, but complete elimination of the side lobes is a very tough job. Hence, an optimum compromise between side lobes, gain and beam width is an important consideration for choosing or designing radar antennas. The side lobe levels of an antenna pattern can be specified or described in several ways. One is the relative side lobe level. That means the first side lobe maximum amplitude to the main lobe maximum amplitude ratio we consider as the RSLR, relative side lobe level. The other one is average level of the side lobes. The third one is median level. Half of the angular space has side lobe levels above it, and the other half has them below that level. This is not so popular. The first one among these things is the most popular parameter of use. You can see how this radiation pattern of the 3D picture is taken into two different planes. One regular vertical cross section is shown separately as a polar diagram in the second one, and the corresponding rectangular graph is shown in the third diagram. Let us see what do we mean by this HPBW. For the given antenna having a cos square theta pattern, we can see how the beam width can be determined. At half power points on both sides of this maximum, you can see that the angular separation is going to be 2 times the 33 degrees. That is, here the beam width is going to be 66 degrees. Let us now see what do we mean by this polarization. It is defined relative to the E field vector of the radiated signal of the antenna. There is horizontal polarization if the E field is horizontal. We say it is vertically polarized if the E field is vertical. Normally, we have the antennas either vertically polarized or horizontally polarized, or grouped into a single one. We call them as linearly polarized. These designations imply the earth reference, but even with airborne or satellite antennas, the same terminology is being used. Here we have the two terms which are very popular in the context of polarization. One is copolarization, the other one is cross-polarization. What do we mean by copolarization? The desired polarization in any particular case is what we call as copolarization or simply copole. The undesired orthogonal polarization is known as the cross-polarization or simply cross-pole. So a well-designed antenna will have cross-pole components at least 20 dB below the copole in the main lobe region and 5 to 10 dB below in the side lobe regions. Here we are going to see another important parameter of the antenna, which is antenna impedance. The complex antenna impedance is given by RA plus JXA. RA is the antenna resistance or simply the radiation resistance of the antenna, and XA is the reactance part of it or the energy stored in the antenna field. And the radiation resistance part is not the complete thing in some of the antennas, because they may also have a small amount of loss across the body of the antenna. In such a case, RA is going to be the radiation resistance plus the loss resistance. Normally, the antenna is connected to the duplexer via a 50 ohm line. Hence, for proper match, the antenna impedance must be 50 ohms even when transmitting or receiving. And how much it is away from this is normally taken through a parameter called voltage standing wave ratio. It is an indicator of how well an antenna matches the transmission line that feeds it, and the equation by which we can calculate this parameter is shown in the slide. The other way of representing the mismatch is by indicating the return loss. The return loss is about the reflected power to the incident power ratio, and it is normally expressed in dB. But there is a direct relation between the return loss and the VSWR. The return loss is expressed in dB, whereas the VSWR is simply a number, and for sample return loss values, the VSWR calculated is shown in this slide. Let us see what are the plus and minus points of the reflector antennas to be used in radars. The different types of reflector antennas used are shown in this. The types are paraboloid antenna, parabolic cylinder, the shaped parabolic antenna, a stacked beam antenna wherein different feeds are stacked before the parabolic reflector to have different beam directions. Then we have a monopulse antenna wherein two feeds are used before a parabolic reflector, and using them you can get some signal as well as different signal. And the last variety is a special type of parabolic antenna known as Cassegrain type, wherein the feed comes through the middle portion or the navel part of the main reflector, and using a sub-reflector we are going to have the complete radiation coming from this antenna system. So these 6 varieties are used for different types of radars. And what is the benefit, or why do we go for a parabolic shape? Here the parabolic reflectors provide maximum available gain, minimum beam width, and simplest and smallest feeds required for this. And here the gain is given by a simple formula as shown in the slide, and the beam width is also calculated very easily when the size of the antenna is given. The basic geometry and operation of a parabolic reflector. For a parabolic conducting reflector surface of focal length f as shown in the diagram, with a feed at the focus, the size and the shape and other parameters can be derived from the basic mathematical equations as shown. And all these things are given through a graph where f by d ratio is identified for different aperture angles of theta. So f by d ratio is the design parameter in these parabolic reflectors. And the main job that will be done is a spherical wave emerging from the focus and incident on the reflector is transformed after reflection into a plane wave traveling in the positive z direction. So by reflection mechanism, here the parabolic reflector is going to convert a spherical wave front into a plane wave front. Reflectors with longer focal lengths, which are flattest and introduce the least distortion of polarization, and off-axis beams require the narrowest primary beams and therefore largest feeds. For example, the size of a horn to feed a reflector of f by d ratio of 1 is approximately 4 times of that of a feed for a reflector of f by d ratio of 0.25. Most reflectors are chosen to have a focal length between 0.25 to 0.5, most popularly around 0.4. As side lobe levels are reduced and feed blockages becomes intolerable, offset feeds become necessary. So you can see the offset beam with a parabolic reflector in the slide here, but the unsymmetrical illumination is the negative point of this. The corners of most paraboloidal reflectors are rounded or metered to minimize the area and especially to minimize the torque required to turn the antenna. The deleted areas have low illumination and therefore least contribution to the gain. Circular and elliptical outlines produce side lobes at all angles from the principal planes. If low side lobes are specified away from the principal planes, it may be necessary to maintain square corners as shown. Parabolic cylinder. It is quite common that either the elevation or the azimuth beam must be steerable or shaped, while the other one is not required for that. A parabolic cylinder fed by a line source can accomplish this at moderate cost. The line source feed may assume many different forms ranging from a parallel plate lens to a slotted waveguide to a phased array using standard designs. The parabolic cylinder has application even where both patterns are fixed in shape. In the diagram here, you can see a parabolic cylinder. Elevation beam shaping incorporates a steep skirt at the horizon, and it will allow operation at low elevation angles without degradation from ground reflection. A vertical array can produce much sharper skirts than a shaped dish of equal height, since a shaped dish uses part of its height for high angle coverage. But the parabolic cylinders suffer from large blockage if they are symmetrical, and they are therefore often built offset. Properly designed, a cylinder fed by an offset multiple element line source can have excellent performance. How about the shaped reflectors? Fan beams with a specified shape are required for a variety of reasons. The most common requirement is that elevation beam provide coverage to a constant altitude. The simplest way to shape the beam is to shape the reflector. Each portion of the reflector is aimed in a different direction, and to the extent that geometric optics applies, the amplitude at that angle is the integrated sum of the power density from the feed across that portion. So, elimination of blockage is done by several means. One of them is shown in this slide here. The limitation is a large fraction of the aperture is not used in forming the main beam. If the feed pattern is symmetrical and half of the power is directed to wide angles, it follows that the main beam will use half of the aperture and have double the beam width. This corresponds to shaping an array pattern with phase only and may represent a severe problem if sharp pattern skirts are required. It can be avoided with the extended feeds. Multiple beams and extended feeds. A feed at the focal point of a parabola forms a beam parallel to the focal axis. Additional feeds displaced from the focal point form additional beams at angles from the axis. This is a powerful capability of the reflector antenna to provide extended coverage with a modest increase in hardware. Each additional beam can have nearly full gain, and adjacent beams can be compared with each other to interpolate angle. A parabola reflects a spherical wave into a plane wave only when the source is at the focus. With the source off the focus, a phase distortion results that increases with angular displacement in beam widths and decreases with an increase in focal length. So the following figures show the effect of this distortion on the pattern of a typical dish as a feed is moved off axis. A flat dish with a long focal length minimizes the distortions, progressively illuminating a smaller fraction of the reflector as the feed is displaced accomplishes the same purpose. So in this figure you can see patterns for off-axis feeds by this. You can see a multiple beam antenna in this, which is normally used in a standard radar. Monopulse feeds. Monopulse is a special type of radar system wherein using a single pulse we would like to get all the target coordinates. So here it is very commonly used with multiple beam antennas for tracking applications, in which a mobile antenna keeps the target near the null and measures the mechanical angle, as opposed to a surveillance system having overlapping beams with angles measured from RF difference data. So in the diagram here, two basic monopulse systems are shown, one for phase comparison monopulse, the other one is for amplitude comparison monopulse. In phase comparison, the two antennas are displaced and the separation between the two beams will give us the phase information and hence the target coordinates. Whereas in the amplitude comparison, one single antenna is going to produce sum pattern as well as difference patterns, and from the difference patterns we are going to get the angle coordinates, and from the sum pattern we extract the range information. So amplitude comparison is far more prevalent in radar antennas. The sum of the two feed outputs forms a high gain, so for target detection, and low side lobe beam. The difference forms a precise deep null at both sides to get the angle information. And azimuth and elevation differences can be provided. If a reflector is illuminated with a group of 4 feed elements, a conflict arises between the goals of high sum beam efficiency and high difference beam slopes. The former requires a small overall horn size, while the latter requires a large individual horns. Multiple reflector antennas. Some of the shortcomings of paraboloid reflectors can be overcome by adding a secondary reflector. The contour of the added reflector determines how the power will be distributed across the primary reflector and thereby gives control over the amplitude in addition to phase in the aperture. This can be used to produce very low spillover or to produce a specific low side lobe distribution. The secondary reflector may also be used to relocate the feed close to the source or receiver. By suitable choice of the shape, the apparent focal length can be enlarged so that the feed size is convenient, as is sometimes necessary for monopulse operation. The Cassegrain antenna, derived from telescope designs, is the most common antenna using multiple reflectors. The feed illuminates the hyperboloidal subreflector, which in turn illuminates the paraboloidal main reflector. The feed is placed at one focus of the hyperboloid and the paraboloid focus at the other. A similar antenna is the Gregorian, which uses an ellipsoidal subreflector in place of hyperboloid. Here you can see the first figure representing the Cassegrain type, the second one representing the Gregorian type. In the Gregorian type, the advantage we get is that blockage is eliminated. Here we are going to discuss something on the feeds. At low frequencies like L band and even lower, dipole feeds are sometimes used, particularly in the form of linear array of dipoles to feed a parabolic cylinder reflector. Other feed types used in some cases include waveguide slots, troughs, and open-ended waveguides, but the flared waveguide horns are most widely used. The varieties of feeds for different types are shown in this slide. One is for a front feed, the other one is for offset feed, the third one is for the Cassegrain feed. Here other types of feeds are shown. One is for Gregorian feed, a simple horn, conical shaped circular one. Then we have a corrugated horn to give wide bandwidth. The feeder in the receiver mode must be point source radiators. In the transmit mode, it must radiate spherical phase fronts if the desired directive antenna pattern is to be achieved. Must also be capable of handling the required peak and average power levels without breakdown under all operating environments. It must provide proper illumination of the reflector with a prescribed amplitude distribution and minimum spillover and correct polarization with minimum cross polarization. Other considerations include operating bandwidth and whether the antenna is single beam, multi-beam or monopulse type. Rectangular waveguide horns propagating the dominant TE01 mode are widely used because they meet the high power and other requirements, although in some cases circular waveguide feeds with conical flares propagating in the TE11 mode have been used. These single mode simply flared horns suffice for pencil beam antennas with just one linear polarization. Shielded aperture reflectors. In some applications, it is desirable to have very low side lobes from a pencil beam reflector. In this instance, considerable improvement can be obtained by the use of metal shielding around the reflector aperture. The typical side lobes are about 0 dBi, which for most reflectors represent a value of the order of minus 30 to 40 dB below the peak gain. With a shielding technique, the far out side lobes can be reduced to minus 80 dB. Shielded aperture reflectors. The simplest approach to shielding the reflector is a cylindrical shroud or tunnel of metal around the edge of the circular reflector. If the aperture is elliptical in cross section, an elliptical cylinder can be used. Radome is another important thing for these antennas. It is to reduce the wind loading and to protect the antenna against ice, snow and dirt. Standard antenna performance parameters are shown in a table here, and here you can see that the off power beam width is quite low, whereas the gain is more than 25 dB at high frequencies between 2 to 13 gigahertz with a antenna in the range of 1.5 meters to 3 meters size. Of course, the front to back ratio is also quite low, definitely greater than 30 dB. And in all these cases, the cross polar component is less than 30 dB. The trade-off between different dish principles is shown here. One with center focus, another one with Cassegrain type, and the third one is offset feeding. And here you can see that the side lobe attenuation is very good with the offset feed, whereas the area efficiency is excellent with the Cassegrain type. For different sizes of the parabolic antennas, the gain observed is tabulated for different frequencies. The reflector efficiency. The efficiency is affected by feed illumination, aperture blockage, reflector surface tolerance. Efficiency is never 100% because of these parameters. What are the unwanted signals we may get with these things? One is scattering, the other one is diffraction at the edges and leading to spillover. That is, the signal will be able to travel onto the reverse side of the parabolic reflector and start radiating in the back side, giving rise to a high F by B ratio. So the F by B ratio for different standard antennas is shown in this slide. Standard parabolic antenna, focal plane antenna and shielded antenna. Here what are the beamwidths we are going to get for different sizes of the antennas at different frequencies is tabulated. What are the benefits we can accrue with the phased array antennas? Let us see now. An antenna array is a configuration of multiple antennas arranged to achieve a given radiation pattern. The types available are linear antenna, where the antenna elements are arranged along a straight line. A circular array, wherein the antenna elements are arranged around a circular ring. Planar antenna is planar elements are arranged over some planar surface, maybe a rectangular one or other types. A conformal array is that an antenna elements are arranged to conform to some non-planar surface, particular to the skin of an aircraft. Array design variables are the array shape, element spacing, excitation amplitude, excitation phase, and patterns of the individual array elements. A phased array is an array of identical elements which achieves a given pattern through the control of the element excitation phasing. Phased arrays can be used to steer the main beam of the antenna without physically moving the antenna. The capability of rapidly and accurately switching beam permits multiple radar functions to be performed, interlaced in time or even simultaneously. An electronically steered beam may track a great multiplicity of targets, illuminate a number of targets with RF energy and guide missiles towards them, perform complete hemispherical search with automatic target selection and handover to tracking. It may even act as a communication system, directing high gain beams toward distant receivers and transmitters. Complete flexibility is possible. Search and track rates may be adjusted to best meet particular situations, all within the limitations set by the total use of time. The antenna beamwidth may be changed to search some areas more rapidly with less gain. Frequency agility is possible, with frequency of transmission changing at will from pulse to pulse or with coding within a pulse. Very high powers may be generated from a multiplicity of amplifiers distributed across the aperture. Electronically controlled array antennas can give radars the flexibility needed to perform all the various functions. Very high powers may be generated from a multiplicity of amplifiers distributed across the aperture. Electronically controlled array antennas can give radars the flexibility needed to perform all the various functions in a way best suited for the specific task at hand. The functions may be programmed adaptively to limit of one of the functions may be programmed adaptively to the limit of one's capability to exercise effective automatic management and control. Now we will concentrate on radar displays. How the final data can be displayed. There are definitely two techniques. One is raw video display. Here the display is the detected and amplified target return signal and the receiver noise. It requires a human operator to interpret the various target noise and clutter signals. The other one is synthetic video. It uses a computer to clean up the display by eliminating noise and the clutter and creating its own precise symbol for each target. Here you can see the two types of displays. One is the raw video output, wherein an operator can only decipher that there are 3 targets at 3 different locations and the 4th one is a ghost, and the signal is projected above the noise floor of the receiver. In the other display, that is by synthetic video, because of the use of a computer, the noise is completely removed and the three different targets are identified separately with the fourth one as the ghost. The search and acquisition radars are the two types we have seen, and they use either a PPI or a sector PPI display. What is this PPI is? It is the plan position indicator. It's a polar plot of direction and distance. It displays all targets for 360 degrees of coverage. Sector PPI is a sector portion of this. It's a polar plot of direction and distance. Displays all targets within a specified sector. Origin may be offset so that your radar position may be off the scope. The types of displays used are A, B, C or E scope displays. There are many other types of displays that have been used at one time or the other, including meters, but those listed here are the most commonly used ones. The different types of displays are shown here: A, B or E, then C, then PPI and sector PPI. What is this A scope is? It's the target signal amplitude versus range or velocity. It displays all targets along pencil beam for selected range limits. It displays tracking gate, usually the raw video. Some modern radars have raw video A scopes as an adjunct to the synthetic video displays. It must be used with a separate azimuth and elevation display of some sort. Some people also call it as R scope or range scope. B scope means it displays the range versus azimuth or elevation. It displays targets within selected limits, displays tracking gate, maybe the raw or synthetic video. Surface radars usually have two displays, one for azimuth, one for elevation, which can result in confusion with multiple targets. C scope, azimuth versus elevation display will be given in this within the selected limits of azimuth and elevation angles. It displays the tracking gate, may display bullseye or aim dot. It may have range indicator inserted typically as a marker along one side, usually displays the synthetic video. Pilot's eye view are very common in modern fighter aircraft heads-up displays for target being tracked. It could be used in any application where radar operator needs an aiming or crosshair view like a rifle scope. E scope, it is the elevation versus range display similar to B scope with elevation replacing the azimuth. Any queries please? Thank you.